So until recently, we used to enjoy the so-called lazy boy approach, and I promise you I didn't coin this term, it was Dave Patterson. I watched a talk of his at Stanford. And pretty much the foundation of the lazy boy approach is that we can sit back, relax, and about every 18 months we'll get a big processor with more transistors, so we'll experience this linear speed up of our code. Well, unfortunately nowadays we get more cores instead of more transistors. So we need to be more careful about our code. We cannot just use the same code anymore. We need to parallelize it and synchronize our code. So this means that our speed up went from almost linear speed up to something like this. So our lazy boy, who was just sitting back and relaxing, now turned into this, what should I say, maybe hacker, but after Alex's talk I would rather say thinker, right? Think and not hack. So it means that we need to be very careful about our code if we would really like to make good use of the multi-core architectures that we have. And this means that sometimes we need to reinvent the very fundamental data structures that we use. So I'll just walk you through an example of designing a shared concurrent hash table here. It's really a toy example meant for a workshop, nothing really fancy, scientific work with lots of buzzwords. So let's start. What's a hash table? It's a very simple data structure that supports three main operations: add, remove, contains. And we know how to build efficient concurrent sets, but unfortunately in the concurrent sets, all these operations take linear time. And in a hash table, we would like to be able to execute them with a constant time complexity. So that's our first problem here. We also want to use a hash function that uniformly distributes the elements in the hash table. So this is a sequential hash table. Oops. Okay. This is a sequential hash table. The hash function is really simple. We take the key modulus, the number of buckets we have. Here we have 4 buckets, and this gives us the position of the element. We have 2 elements, we add another element, we add one more, and we have a collision of bucket 0. Now, to be able to preserve the constant time complexity of these operations, we cannot grow a bucket forever, right? Because we keep on adding more elements, we have more collisions, so eventually we need to resize, otherwise we wouldn't be able, as I said, to preserve the constant time complexity of all these operations. So right, we resize by expanding, creating a new table, changing our hash function a bit. Now it's, we take the key modulus 8, because 8 is the new bucket number, the number of buckets that we have. And we need to redistribute some of the elements according to the new hash functions that we have. So I believe that we are all familiar with all this behavior. This is the sequential behavior of a hash table. So how do we build an efficient concurrent hash table, shared concurrent hash table? This is the problem that I would like to entertain you with here today. Well, for example, it's a well-known approach to use log-free linked lists. Maybe you've heard this term. Michael and Scott from the University of Rochester, they came up with it about 15 years ago. So currently it's well known, and we can just use a single array and a linked list, a log-free linked list for each of these buckets. So this seems like a fairly reasonable approach. Now, I just want to clarify that by saying log-free, I don't mean that we're not going to use logs. Formally defined, log freedom is a progress condition where we guarantee that there is at least one thread that makes progress in a finite number of steps. Well, this implies that we cannot use logs, because if we do, we would break this progress condition. But formally defined, it is a progress condition. So let's take a look at some simple circles. So we'll create an array, we use a log-free linked list for each of the buckets, and initialize it, and whenever we need to add an element, we'll compute the hash, add it to the linked list, so we're done, and our implementation of a concurrent hash map was a no-brainer. Well, not that easily, unfortunately, because I forgot to tell you how to resize. So as you can see from where I'm going, the real difficulty of designing a concurrent hash map is the resizing function. So how do we do a resize? Well, before we do that, just wanted to mention that studies show that the typical mix of 99% land, 1% remove. And since we are the 99%, we really care about the contains in the add more than the remove. But this is just something that's going to guide our design decisions. So here is the first suggestion. Let's just coarse-grained locking. Use a global lock. We'll lock the whole hash table whenever we need to resize, and lock it when we're done. You all sense that most likely this wouldn't be the conclusion of this talk. Certainly, using a global lock deserves some respect. It's so simple and it's very hard to mess up. But unfortunately, the single lock is a point of contention, and it also reduces the parallelism, the amount of concurrent operations that we can execute concurrently. So these are two separate issues that I would like to emphasize this. One is contention, and the other is reduced concurrency on the hash table. So let's try to be clever. How about fine-grained locking? We'll just use a dedicated lock for each of the buckets. Adding an element is easy. We just acquire a lock to the bucket, add the element, release the lock. So simple. How do we resize? Well, simple again. We acquire all the locks in ascending order, validate the pointer to the tail pointer of the hash table, and then we can resize. We create a new table, move all the elements, and then what do we do with all the logs that we have? It's not really easy to resize the array of logs that we have, because if we do that, we need to disable the old logs, send interrupts to all the threads that are currently waiting on them. So unfortunately, that's not going to work very well either. We need to come up with something better, because otherwise we need to use these logs. They're called striped logs, meaning many buckets have to share a log now. So we pretty much have to predefine the number of logs we're about to use in the system. And this is really hard to tell how many logs we need, because if there are too few, we create contention. If there are too many, the resize function has to play with all these logs every time we resize, and it has a higher overhead. However, that's probably one of the best blocking solutions that we've known. That's implemented already in that Lee's, I think, implementation that's already part of the Java concurrency package. But we can improve this further. One way to improve it is to observe that if we implement contains, multiple contains operations, they don't have to block each other. We can execute several of them in parallel. So we can do that. We can do that by introducing a reader-writer lock, a read-write lock. We can have all the readers trying to acquire a read lock. When a writer comes in, we have to wait for all the readers to train, acquire the write lock. We were not going to allow any more readers and perform our update to the hash table. We can do even further optimizations by doing optimistic synchronization. In fact, we observe that the contains doesn't always have to acquire the read lock. We can just optimistically search the hash table, and if we find the element, it means we're done. So we won because we managed to execute this operation without acquiring any logs. The problem is, what happens if we don't find the key? Well, it's one of two possible scenarios. One, the element is probably not there, or two, we could be a victim of a resize. But since we don't know which one of those it is, we still need to acquire the read log and execute the operation all over again. So the optimistic synchronization approach makes sense only if most of the time we find the element we're looking for, and also we don't resize as often. Otherwise, this just incurs more overhead. So by thinking about what could be a good solution of the hash table problem, we realize that the real problem is the resize operation, and this implementation of a resize that stops the whole world. So our desired solution is it possible to come up with a hash table where we perform the resizing incrementally without having to log the whole data structure? Such algorithms are known as log-free algorithms. So let's think what we need to do in order to implement one of those. Well, when we resize the hash table, we need to create a new table, remove a bunch of elements, remove them from the old locations, the old linked lists, and place them in new linked lists. And we need to do that by using only atomic operations. This seems impossible, so it seems like this solution is doomed. we can just give up and say we can't implement this hash table in a log-free way, just using compare and sets in the atomics library in C++11. Well, let's not give up that easily. There is a way. By turning the idea on its head, how about if we decide not to move the elements? How about if we just keep a single linked list, ordered linked list, where we store all the elements? And you'll be saying, you'll tell me, wait a minute now. Now, what about the constant time complexity, right? Because it's a linked list, so this seems like linear complexity, not constant time complexity, right? Well, here is the solution. We still have buckets, but each pointer becomes a shortcut to a particular location in this linked list. Now, the whole logic is the way we order the elements in the linked list. Let's assume this is a hash table containing only one bucket. When we need to resize and split this in two, we just redirect a pointer to the middle of this linked list. And when we need to split it again, we do it over again. Now, you will ask me, how do we order the elements so we can achieve this magic property? Well, here's an idea. How about if we order the elements according to their least significant bit? So the elements in the first bucket have least significant bit 0, and the elements in the second have a least significant bit 1. If we have more buckets, then we take the bottom two least significant bits. So I think you get the idea. The idea is that if the table has a size 2 to the power I, then the bucket index, the bits that determine where we should place an element, is I least significant bits. So this is the index. And when the table splits, counting backwards, the bit at position I plus 1 is going to determine whether the element stays in the old bucket or goes to the new one, but without physically moving the elements. And this is the magic. If we just look at the keys and their positions in the table, well, lo and behold, it's exactly, not surprisingly, we take the bit representation of every element and reverse it backwards. So this is, in fact, work that was proposed by Shavit and Shalev some time ago, and we have now a team of research assistants at Texas A&M working at University of Central Florida, working on creating an STL-like library of such log-free containers. Well, there is yet another problem that you probably noticed. Some of the elements in this hash table are pointed to by two different nodes. For example, whenever we have, let's say, 9, it's pointed to by the previous node and also by the pointer of bucket 1. So how do we take care of this problem? Because again, we're using only compare and swap operations. That's not that hard. We can just introduce a sentinel node that stays there. We don't have to move it. We just have to do a little bit more of bit arithmetic by using the most significant bit here to designate these sentinel nodes. So since I don't want to take a lot of time, let's fast forward to please look at some performance graphs. These experiments were performed on a Sun Enterprise system with 30 processors. If you haven't had a chance to work on one of those, it's a cache coherent NUM architecture. We compared the log-free solution that we just saw versus a fine-grained optimistic approach that's already part of the Java concurrency package. We translated this into C++. The mix of operation is 88% contains, 3% add, 2% remove. So first of all, we wanted to find the optimal number of logs for the logging solution, because as we said, we can pick different logs and we have to predefine those. So for this particular setting, we found out that using 64 logs performs best. Again, there is a trade-off here. If we use less logs, we have more contention, and if we have more logs, the resize operation is going to take longer. the log-free versus the log-based approach, we found out that the log-based approach reaches its peak at about 24 threads, and after that, pretty much stays the same. The performance graph doesn't deviate much, doesn't experience the deviation caused by the architecture's critical path, and that's probably because we never reach a high degree of parallelism here. We reach a certain bottleneck that's caused by the use of mutual exclusion. And in the majority of cases, the log-free solution, we found out that it scales better. And finally, talking about scalability, at my work at Sandia Labs, it's fashionable to talk about exascale, meaning using many threads, probably hundreds of thousands of threads and cores at the same time. But it's really hard to predict what's going to really happen if we have such a machine. Pretty much everything is an open area of research, including programming models, fault tolerance, the trade-offs among power, performance, and cost. And if we don't understand this, we realize that we'll end up with a machine that we probably won't be able to turn on, or probably a machine that's going to turn itself off because of all the failures that we experience. And at the very best, we'll see extreme diminishing returns. So we built this tool that's called the SST Structural Simulation Toolkit that we use as a communication and synchronization simulator. Well, before I joined the team, it was just a communication simulator. We used to simulate MPI, but now we have the ambition to make it a synchronization simulator as well. We model applications by creating the so-called model skeletons by capturing only the communication patterns. And we even do that automatically right now using the ROSE compiler. We are able to take a real HPC application, derive its communication skeleton, and run it on this simulator. We have some funding from the DOE Oscar program to perform simulations of combustion codes and also do HPC hardware software co-design. That's a hot area of interest. So, any questions? Thank you for your attention.
Problems with concurrent hash tables often is that it's difficult to decide when to resize because it's difficult to actually keep account of the number of elements in the table because otherwise the increments will contain. Do you have a solution to that?
So let me make sure I understand your question. Your question is that the problem is that it's difficult to keep account of the number of elements. In this particular case, we really need to keep account of the number of elements in each bucket because the resize is triggered. I mean, the resize decision can vary, but we can either decide to resize when one single bucket reaches a certain threshold or when a number of buckets reach this threshold. I'm not sure whether this is exactly what
Oh, okay, so you only look at the maximum bucket size to make the resize decision.
Yes, this is in this particular solution, yes.
Okay. That works.
May I ask a question about the graph that we saw like 2 or 3 pages back?
Yeah.
That one. So it seems odd to me. Why do you have some dips where increasing the number of threads actually decrease performance?
Yes, that's a very good question. I don't know. Probably it's because we have 30 processors here. So afterwards, probably the performance really is impacted by the scheduling decisions.
But one of those dips is at 20.
True.
Okay.
So we can observe that probably the performance here fluctuates more, but with the log-based approach, we reach a certain limit and we cannot go higher than that anymore.
More questions? Thanks.
Thanks.